Hey there, science fans. Have you ever wondered how substances change and transform? That's the magic of chemistry. From the food we eat to the air we breathe, chemistry is happening all around us. One of the most fascinating aspects of chemistry is understanding how much of a substance is involved in a chemical reaction. That's where the quantitative part comes in. In this wild ride through the world of atoms and molecules, we'll uncover the secrets of chemical change and learn how to measure and predict the outcomes of chemical reactions. Get ready to dive into the exciting world of quantitative chemistry. It's going to be an explosive journey. Imagine the smallest thing you can possibly think of, like a grain of sand. Now imagine something even smaller than that, something so tiny you can't even see it with a microscope. That's an atom. Atoms are the fundamental building blocks of all matter in the universe. Everything around us, from our bodies to the stars in the sky, is made up of these tiny particles. Atoms are incredibly small, but they are powerful. They combine and interact with each other in amazing ways, creating the incredible diversity of substances we see in the world. But how do we keep track of these minuscule particles? How do we measure something so small? That's where the concept of atomic mass comes in handy. Get ready to unlock the secrets of atomic mass. We know that atoms are incredibly small, but did you know that they also have mass? It's true. Even though we can't weigh a single atom on a scale, scientists have figured out a way to determine their relative masses. Atomic mass is the mass of an atom compared to the mass of a standard atom. The standard atom used for comparison is carbon-12, which is assigned an atomic mass of exactly 12 atomic mass units, or AMU. For example, a carbon atom has an atomic mass of 12 AMU. This means that a carbon atom is 12 times heavier than 1/12 of a carbon-12 atom. Atomic mass is a fundamental concept in chemistry because it allows us to compare the masses of different atoms and molecules. Stay tuned to see how. Now that we know how much an atom weighs, let's talk about how we count these tiny particles. Counting atoms individually would be an impossible task. Since atoms are so small, it would be impossible to count them one by one. Imagine trying to count grains of sand on a beach. That's where the mole comes in. This concept simplifies the process. A mole is a unit of measurement used in chemistry to express amounts of a chemical substance. It's like a bridge between the microscopic world and the macroscopic world. It's a really big number. So big, in fact, that it's hard to visualize. 1 mole is equal to 6.022 times 10 to the 23rd particles, which is known as Avogadro's number. This number is fundamental in chemistry. Think of it like a dozen eggs. Just as a dozen always means 12, a dozen always means 12, right? Similarly, a mole always means 6.022 times 10 to the 23rd. Similarly, a mole always means 6.022 times 10 to the 23rd. This consistency helps chemists make accurate calculations. So, if we have 1 mole of carbon atoms, we have 6.022 times 10 to the 23rd carbon atoms. That's an astronomical number of atoms. The mole is a crucial concept in chemistry because it allows us to relate the mass of a substance to the number of atoms or molecules it contains. This relationship is essential for understanding chemical reactions. Get ready to dive into the delicious world of moles. Understanding this concept will make chemistry much more intuitive and exciting. Section 5: Composition by mass. What's in that substance? Have you ever wondered what makes up your favorite snack or drink? Just like a recipe tells you the ingredients and their amounts, percent composition by mass tells us the percentage of each element in a compound. For example, water, H2O, is made up of 2 hydrogen atoms and 1 oxygen atom. The percent composition by mass of water is hydrogen, H 11.19%, oxygen, O 88.81%. This means that in 100 grams of water, 11.19 grams are hydrogen and 88.81 grams are oxygen. Percent composition by mass is important because it helps us to identify and characterize different substances. It's like a chemical fingerprint. Section 6: Molar mass, weighing out moles of substances. We've talked about atomic mass and the mole, but how do we connect these two concepts? This is a fundamental question in chemistry. That's where molar mass comes in. It serves as the bridge between the atomic scale and the macroscopic world. Molar mass is the mass of 1 mole of a substance. This is a key idea that helps us understand the quantity of material we are dealing with. It's expressed in grams per mole, making it easy to relate to everyday measurements. To calculate the molar mass of a compound, we simply add up the atomic masses of all the atoms in its formula. This is a straightforward yet powerful tool. For example, the molar mass of calcium chloride, Kcal2, is calculated by adding the atomic masses of calcium and chlorine. Calcium Ca has a molar mass of 40.08 grams per mole. Chlorine Cl has a molar mass of 35.45 grams per mole. Since there are 2 chlorine atoms, we multiply this by 2, giving us 70.90 grams per mole. Therefore, the molar mass of KCl2 equals 40.08 grams per mole plus 70.90 grams per mole, which totals 110.98 grams per mole. Molar mass is a crucial concept in chemistry because it allows us to convert between mass and moles, which is essential for many chemical calculations. This conversion is vital for understanding reactions and stoichiometry. Stay tuned for more exciting calculations and deeper insights into the world of chemistry. Section 7. Solutions, mixing things up in chemistry. In our everyday lives, we encounter solutions all the time. From the air we breathe to the beverages we drink, solutions are everywhere. In chemistry, a solution is a special type of mixture where one substance dissolves evenly into another. The substance that dissolves is called the solute, and the substance that does the dissolving is called the solvent. For example, when we stir sugar into water, the sugar dissolves completely, forming a sugar solution. In this case, sugar is the solute and water is the solvent. Solutions are essential in many chemical reactions because they allow reactants to mix and interact more easily. Section 8. Concentration of solutions. How strong is that drink? Have you ever noticed that some drinks are sweeter or more tart than others? That's because they have different concentrations. Concentration refers to the amount of solute dissolved in a given amount of solvent or solution. There are many ways to express concentration, but one common way is molarity, or M. Molarity is defined as the number of moles of solute per liter of solution. For example, if we dissolve 58.44 grams of sodium chloride or NaCl in enough water to make 1 liter of solution, we have a 1 molar or 1 M solution of sodium chloride. Understanding concentration is essential in many areas of life, from cooking and baking to medicine and environmental science. Section 9. Stoichiometry, the recipe for chemical reactions. Just like a recipe tells us the exact amounts of ingredients needed to bake a cake, stoichiometry tells us the exact amounts of reactants and products involved in a chemical reaction. It's a precise science that ensures we get the right results every time, just like following a recipe ensures a delicious cake. Stoichiometry is based on the principle of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction. This fundamental principle is crucial for understanding how reactions work. This means that the total mass of the reactants must equal the total mass of the products. No matter how the substances are rearranged, the total mass remains constant. To perform stoichiometric calculations, we use balanced chemical equations. These equations are like the instructions in our recipe, guiding us through the process. A balanced chemical equation shows the chemical formulas of the reactants and products, as well as the coefficients that balance the number of atoms of each element on both sides of the equation. These coefficients are essential for ensuring that the law of conservation of mass is upheld. Stoichiometry is an essential tool for chemists because it allows us to predict the amount of product that can be formed from a given amount of reactants, as well as the amount of reactants needed to produce a desired amount of product. This predictive power is invaluable in both research and industrial applications, making stoichiometry a cornerstone of chemical science. Section 10. Limiting reactants. When ingredients run out. Imagine you're making sandwiches for a party and you have 10 slices of bread and 6 slices of cheese. Even though you have more bread, you can only make a maximum of 3 sandwiches because you'll run out of cheese. In this case, cheese is the limiting ingredient. Similarly, in a chemical reaction, the limiting reactant is the reactant that is completely consumed first, limiting the amount of product that can be formed. The other reactants are said to be in excess. To determine the limiting reactant, we compare the amount of each reactant to the stoichiometric ratio in the balanced chemical equation. The reactant that produces the least amount of product is the limiting reactant. Understanding limiting reactants is crucial in many industrial processes because it helps to optimize product yield and minimize waste. Section 11, Conclusion. Chemistry is everywhere. Congratulations, science explorers. You've journeyed through the fascinating world of quantitative chemistry, uncovering the secrets of atoms, moles, and chemical reactions. From the tiniest atom to the largest industrial process, chemistry is all around us. By understanding the quantitative aspects of chemical change, we can make informed decisions about the products we use, the foods we eat, and the environment we live in. So, keep exploring, keep questioning, and keep the spirit of science alive. The future of science is in your hands.